Okay, here's another example of an experiment. Some outcomes is I choose 5 numbers with replacement from 1 through 64, keeping track of the order. So, for example, just a list of integers. I could have duplicates here. I don't in this when I put. So S is 1, 60, 50, 37, 47. So just means an outcome. This just means an outcome. The first choice was 1, the second was 60, etc. The size of this is 64 to the 5th, which is 2 to the 40th, so that's about a trillion outcomes. And if I say let E be the set of all outcomes with 3 or more digits appearing in order, for example, 61, 3, 41, 41, 41, then that is an event. Okay, so I can let E be the set of all of those. So S is obviously huge. E is also big. Okay, these are just some examples. Okay, they're not meant to confuse you. So, but maybe they did. Hope not. Okay, so we're getting there. We have sample space and event. What's another one? Let's do another one. E. Suppose I have E, just another short one. Roll 2 dice. And observe order. Okay, then what's the size of S? Well, die have 6 sides, so the size of S is 36 different outcomes. And I could have E be the event, say, for example, let E equal the set sum of the dice is greater than or equal to 10. So then E, I could list these, is would be, let's see, 4, 6, 5, 5, and 6, 4. You notice there's not 2 of these. There's just one way to get 10 that way. And, oh, I said at least. Sorry. At least 10. So those are all equal. And now I need the ones that are bigger. So there's that, and still that. Okay, so their size of E is 6. All right, okay, so several examples. So far, so good. Now, notice so far we haven't defined probability. We're just talking about the space it really operates on. So, yes, we are getting there. All right, so a little more. So really there's this big overlap with this and set theory, as you can see. I mean, events are sets. Sample space is sets. And that's what the probability, which is a function, operates on these sets. So there's this nice overlap between probability and set theory. Okay. So we got to define some operations on these sets. So definition. Let E and F be events. Okay, be events. So I could just go like that. Be events in S. Then EF, E union F, and EC are also subsets. Are also events or subsets of S. Okay, and defined as follows. Okay, so in other words, I can start with 2 events in S and then perform such operations on them. Or in the case of EC, we'll start with 1 event and perform an operation on it. So So let's define them. So first of all, one, let's say EF is defined to be as follows. EF is equal to, we can just do it like this, is equal to the set S in S such that what? Such that S is in E and S is in F. All right, this is called the intersection, and sometimes it's written E cap F with the upside down U, but usually it's written this way, just like multiplication, so EF. So any element in S that's in both E and F is in EF. Okay, what about, we'll do some examples after. E union F means it's all outcomes. It's a set of outcomes in S such that S is in E or S is in F. And finally, EC is equal to S in S such that S is not in E. Okay, that's it. Okay, so that's it. There's not a lot of other operations on these, although we can build on them with more events and etc. So suppose we go back to, let's see, which one? I don't even remember now. Yeah, okay, I think we can do it with it. Suppose we go back to example A, flip 2 coins. So we had S was all 4 possible ordered outcomes, and we let E equal at least 1 head and F at least 1 tail. Then can we list E? Well, E, yes, we already did this. E has 3 elements in it, right? The ones with at least 1 head. So I'm just going to go ahead and write this. So what's EF? I need at least 1 head and at least 1 tail. So this would just be, these are in both. I never actually wrote F down. But. And what's E union F? Well, this is S, right? Everything is covered then. And finally, EC. Well, this means no head. So this is a new one. So this is just the single outcome, TT. Okay. All right. I think you're familiar with this basic set stuff, but if not, now you know. All right. Let's see. Some properties that follow pretty naturally from these are some properties, you can check these pretty quickly, are E union F equals F union E, EF equals FE, and kind of a distributed property too, which is associativity and also distributive. So I also have EFG, can do this either way, equals EFG, also for unions. Okay, and then also if I have E, say F union G, this is EF union EG. Okay. Yes, stop here. So yeah, not the other one, but this one. So if I multiply a union, if I take the intersection of E with the union, it's the same as taking the intersection of E with each and the union. Okay, so these are our properties. There are other ones you can find. You can build other ones out of these. Maybe using three, sure. So these are the main ones I can think of right now. So as we go, though, I mean, it's normal to be expected to go back to the basic definitions and be able to understand why some operation or equation is true or not. Okay, I think I'll get on to the next. There's a nice property coming up next about combining all of these called De Morgan's laws, and we'll do that now with a little proof, but I'll do that on the next video.